Pinned picture, okay? Maybe. 41 seconds.
I'm applying for a new film loan. Go by the name of Vector. It's a mathematical term. Quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
Okay. Just showing you that because a vector has what, guys?
Direction, magnitude.
Okay, and that's kind of the name of the game today, okay? Okay, so if you already filled in those blanks, a vector, we represent it with an arrow typically, and it has, like it said, both magnitude and direction. You're probably thinking, well, what's magnitude? It's kind of like its units, like velocity, force, newtons, miles per hour. It's like a unit, okay? So a vector. Here, I think on the next slide, are just some examples. A lot of like pilots use these, meteorologists use them. I guess car accidents. I was trying to find some more applications last night. Car accidents, they use vectors to figure out if a car is going east at 30 miles an hour and then it hits like T-bones another car going this way. They represent vectors. But anywho, apparently they are very applicable in physics. So here's the map. Or meteorologists would use it, I think, for like wind directions for a tornado. Is what I'm guessing. But do you guys see all the little individual vectors in there? Right? Showing the direction of the wind. And maybe the different colors would be, like there'd be like a key that said, if it's red, it's going at like 30 miles an hour or whatever. I don't know. But it sounds good though, doesn't it? That sounds like a decent little change. But magnitude, let's fill in some blanks here. All you gotta think about is it's the length. So for our purposes, we just kind of scratch the surface of vectors, and we're just gonna find out how long a vector is, how long your arrow is, and its direction by using trig, okay? That's all we're doing today. But to find the length, you start at its initial point to its terminal point. And an easy way to remember that, what does terminate mean? Word end. So here's where I start, the initial point. Here's where I end. And we'll find the length of it by doing Pythagorean theorem today. We'll draw in a little right triangle. A squared plus b squared will give us our magnitude. And then direction is the angle that is formed with the positive x-axis. So that's kind of goofy because do we all agree this is a vector here, AB? There's my vector. Okay. What it means by positive x-axis, would we all agree that these numbers on the right side of the origin are the positive numbers? So this is your positive x-axis. So to find this length here, or this angle here, all we would do, draw in a right triangle, and then we'd use trig. It ends up being the tangent function. Okay? It's overwhelming, kind of. I know it's all new, but it's very quite simple once we get into it. And the last little vocab thing we need to check up on before we get started is component form. And it's just a way to describe how far over a vector goes and how high up. So if I change in this way, and then if I could like go up. I change in your horizontal and your vertical. And it's written as x, y. With those weird little parentheses, they look like V's on their sides. So let's just pretend that this terminal point was at 9:12. So from the origin, how far over did I go? 9, that was my change horizontally, and how high up did I go? 12. So if I wanted to write the component form of this vector W, it would just be 9, 12. This is an easy example because it starts at 0, 0, but we'll do more so you can see that how it works otherwise. Okay? Like right now. Let's try to write the component form of these two vectors. So let's start with PQ. On this one, let's just count. So let's just start here at P. How far over do I have to go to get to Q? 2, right? But if I went to the left, positive or negative? Negative. And how far down? 4, but since I went down, it's negative 4. So we're just finding how to get from where you start to where you end. On DC, let's do it without counting on the graph, just in case you didn't have graph paper, you would know how to do it. All you're doing is subtracting, starting with the terminal point and subtracting your initial point. So on DC, would I start with 0 or 4? 4, right? I'm going to take 4 and subtract 0, just your x coordinates here. And then for your change in y, 1 minus negative 1. So what do we get? That should be a positive 1, guys. Sorry. Positive 1. That's not right. Would we have gotten the same answer if we would have switched our ordered pairs? Let's just try just to see. You guys don't have to write it down, just look up here. Let's say we started with 0, 0 minus 4, and negative 1 minus 1. But though, are these the same? No, so that's why you always start with the terminal point, okay? So how do we feel about finding component form? We get it? We're just finding the change in our directions, okay? Okay, now we are asked to find both the magnitude and direction. So first steps first, just graph it. Let's just see what we're dealing with. So just graph these 2 points and see what our vector looks like. Is that what you guys got for your vector? Something like that? Okay. Again, we're just going to do Pythagorean theorem. So let's draw in a right triangle so we can use Pythagorean theorem to find the length of RT. And if you can just count, gold star for you, but I'm going to draw it in so you guys can see the right triangle. One, two, three, four, 5. 1, 2, 3, 4, 5, 6. So what you guys got? And now just 5 squared plus 6 squared equals x squared, c squared, whatever variable you want to use. Hopefully we're getting what, square root 61? Approximately what, Skylar? 7.81. 7.8? Yeah. That sounds like a good answer to me. Everyone Good? Okay. So can we go back a slide here, guys, and let's look at this. So to find direction, it says the angle that is formed with the positive x-axis. So you can take a vector and you can shift it wherever you want on a coordinate plane and it's still the exact same vector. So to make our lives easier, we are going to shift our vector so it's in standard form, which just means it starts at 0, 0. Okay? So we're going to take a moment and we're going to take R and put it at 0, 0. Just let's do it this way. Okay? So I'm going to move my R to 0, 0. And then I have to count over 5, up 6 to get to T. So you can either erase the original one or draw over it, whatever works for you. Yeah, some of you'll be able to do that, but some of you won't be able to see where your angle is, and you'll get the wrong answer. Okay, so if it works for you, you can do it the other way, but for today, I think I'm going to teach it this way. Okay, now I'm going to redraw in our right triangle here. Here's 6, here's 5. And now we need to find the angle that it makes with the x-axis right here. So that's just trig, right, guys? What's 6 with respect to x? Opposite, and what's 5? Adjacent. So what trig function uses opposite adjacent? Tangent. Tangent of x equals 6 over 5. And find angles, remember to use the inverse functions. What did anyone get? 50.2? That kind of looks like 52 degrees if you look at it. Sounds about right. Perfect. Okay, let's try another one. If they're not clicking yet, I promise they will. Just try another. So start off by graphing your points so you can see what direction your vector is going. Yep, so finding the magnitude is easy, right? We're just going to draw in a right triangle and Pythagorean theorem. Did you guys find 7 and 5 to be your side lengths? Okay. What did you guys get approximately for your magnitude? 8.6. Wonderful. Okay, so now remember we're going to put it in standard form, so we have to shift our S to 0, 0 and redraw it. anyone in geology doing the earthquake? And they're probably not doing fresh, but take geology if you can. It's a fun class. Anywho, let's go back to this. Okay, we gotta find our angle here, so what do I have to use? Trig. I promise, it always ends up being the tangent function. So tangent of x equals what? 5/7. X equals 35. Okay, now this is the part where I want you to always graph your vectors, because on your calculator your answer is 35.5. But look, guys. You start here. This is important. You guys should all look up here. You start here, but think, I have to go all the way around till I get to this vector here. So here would be 90 degrees. Here would be 180, so that would just be a straight line. Plus another 90 is 270. So how am I going to figure out what this piece is here? Right, so if I went all the way around, I get 360, but I know what this part is. We just found this to be what? 35.5, so we're going to subtract 360 and 35.5, and that's actually our direction. You have to find it to our vector, because you always start here, and you have to go counterclockwise till you get to your vector. Does that make sense? Start here, haven't hit it, haven't hit it, haven't hit it, haven't hit it. Oh, I got it. And I know if I went all the way around the full circle, it's 360. We found this chunk right here to be 35.5, so we can just subtract, find out what our direction is. So what is our answer? So I guess, guys, a way to think about this is if you get a vector, when you put it in standard form that goes in either the third or fourth quadrant, it's going to be greater than 180. Does that make sense? Let's try another one. Try another one. It's on the next page. Someone remind me, what is magnitude? What was the blank filled in? The length. Do I even have to do Pythagorean theorem here? Can I just count? How long is it? 6. Easy peasy, lemon squeezy. Okay, put it in standard form. P goes here. Oops, one too many. What is our direction? Did I go up any? No, so it's just 0. Just 0. What if PQ went like this? What would it be? What would your angle be? 90. What about right here? 180. What about this guy? 270. Does that make sense? Maybe. Okay, we have one last kind of problem to go over. And that's when you add and subtract vectors. There's no easy way other than just try to be as accurate as you can when you sketch them. It's just a sketch, okay, guys? So if I want to add vector A to vector B, let's go like that right now. Why don't you label this for me? Redraw vector A and give yourself some space. Try to be as close to the same direction it's going and about as long as it is. So there's my vector A. Now I'm going to add vector B. So I'm going to start in the same place I started with A and just draw B. So I'm going to draw B from here. Now this is called the parallelogram method. We're going to finish off our parallelogram here. If you guys remember what that is. I'm just going to sketch in what my parallelogram would look like. Remember, your sides should try to be parallel and congruent, opposite sides. And then your actual answer is the vector that goes from where you started from to the opposite corner of your parallelogram. That is your end answer, the resultant vector. What's that? Yep, well the sum, that's adding, right? Now we're going to do the difference, we're going to subtract, now we're going to do a different problem. So that was our sum. Summing means to add. Now we're going to find the difference. So again, start with A. So when you subtract something, you just draw it in the opposite direction. So do you guys see how B is going this way? I'm going to draw B going the opposite way. So here's where I'm starting, but instead of going to the left, I'm going to draw it going to the right. And then again, you're just going to draw in your parallelogram. Something similar to that, guys? Anything? Getting kind of close? Can you try the next one on your own, adding C and D and then subtracting them? See how it goes?
magnitude.
Oh man, this one got wonky. Sorry, guys. Something like that, ish, ballpark, close. As long as your adding is going this direction and your subtraction one's going more this way, we're okay for today.